Very good afternoon, all. So, I hope all of you are keeping well, doing well, and basic programming of graphs has been started. So, last time we have discussed DFS, BFS, their implementation analysis. Just before I start with the discussions for the today, let me just quickly have a recap of DFS and their algorithmic implementation using a global arrays. So just I said that we are going to implement a DFS using global array of a visited and a parent. So this is the node structure, and then I have a visited array taken, parent array taken. Then my DFS, I have the two parts. One is your main DFS function. So there I initialize here like this, and then I'm going to check if visited I is false. So a DFS visit is called, and here is my DFS visited. In this, as soon as I traverse it, it is treated as visited I equal to 1. And then I have the normal logic, which we have already discussed, and their parent is also updated as soon as I get some adjacent vertex. So I find which is the next adjacent vertex, and accordingly do this. The purpose of showing this is those who have not done programming, they can understand and improve. And those who have done, they can have also clarity that what can be the various ways. And secondly, we should be able to revise and recall how DFS works, because today's discussion now will require, in fact, all other discussions in the future will require some traversal algo, either DFS or BFS, and the clarity of working will be highly desirable to understand any of the further logics which we are going to see. So resuming from here, now let me start with today's discussions. And today we have a very interesting topic, and we are going to see various algorithms where these graph, DFS, BFS, etc. are going to play, but we are going to solve some real life situations. So in NIT Kurukshetra, in your classes, or like in third semester, you have effectively 6 core courses which you are studying. You are not having much choice. All these courses are must, and in same time you have to study. In most of the foreign universities, you have to effectively register for the courses. In most of the BTech courses, etc., or many other UG, PG courses, you have to do a course registration at the start of every semester. Effectively means choose your courses which you are going to study, which you want to study in this semester, to be studied in this semester. So there is a lot of flexibility that you can study courses based on your time availability, how many courses you want to study at this semester, etc. So like there you might be said in third semester, okay, these 2 core courses are a must, and then you can have minimum, let's say 1 more, or maximum, let's say 4 more or 3 more, or maybe let's say you are told maximum you can have 4 more. So you have a flexibility whether you want to take in this semester only 3 courses or you want to take 6 courses. And that also you have to have which courses. Options could be there. Options for the courses. Like say, you might say that at this semester I am very busy, or that subjects are difficult. So you might choose that, okay, database, and I don't want to study database and algorithm at the same time. So database or algorithm, one of these I will take, and maybe later I will take the other subject. Of course, your degree might get slowed, so you might have a slow pace for the coverage. Instead of 4 years, you might complete in 5 years or so. So foreign universities do allow. So at the start of the semester, you have to choose. Then the question will be, are you allowed to leave these or one of this? Yes, you might be allowed, but sometimes you might not be, because the courses choice is effectively dependent because of they have a dependency among each other. So there are a lot of subject or course dependencies, and we say normally there is going to be a prerequisite requirement of certain courses. So prerequisites you must have studied, only then you can register for a course. For example, I say in BTech degree in any semester, C programming can be started without prerequisite. But if you want to study data structure, you must have studied C programming. If you want to study algorithms, you must have studied C programming as well as data structures. So I'd say for algorithm, both are prerequisites. Then I could say, okay, once you have studied algo, only then you can study OS. For studying OS, you must have, let's say, I should have studied the digital system design initially without any prerequisite. After digital system design, you are allowed to study computer organization and architecture. Say, if you have studied COA also, only then you can study OS. Similarly, if you have studied COA, you can go for an advanced architecture course also later. If you have studied COA, then you can also go for microprocessor course. And similarly, I say, if you have studied OS plus this subject, maybe I say for reading computer networks, I must have studied, let's say, this course. I must have studied, let's say, I call some other course. They have some dependency over CM, some other course, etc. So we can see there are a lot of prerequisites. Like I say, this diagram says for OS, prerequisite is algorithm as well as COA. For MUPI, prerequisite is a COA. For COA, prerequisite is digital system design. For this course, sorry, for both these courses, there are no prerequisites. So you can register for this. So when you are registering, you will be checked whether you are allowed to register for this course, whether you have completed prerequisites. So your university registration software will check all these things for the prerequisites. How it will check and how student will come to know, you have to all know all these things. So for such situations, things like topological sorting in an excellent algorithm, which is very useful for such situations. So we are going to study to start with topological sorting. Well, when I say over graphs, so when I have a graph, and if graph is DAG, where DAG stands for a directed acyclic graph. So over DAG, we can do some sorting like topological. Acyclic means no cycles. What does a cycle mean in a graph? Like if I have some vertex A, I have some vertex B, say I have some vertex C. If I have a connection like this is a cycle. Like I can see, this way I can have the total rotation. So always I can have from any node to any node going like this. Similarly, maybe I can say, let's say I have F, I have a G. From F to G also there is an edge. From G to F there is also an edge. So this is a cycle. So obviously, two or more vertices can be in a cycle. Self loop also can be a cycle, but we rarely bother about this. So this is what is a cycle. So I say if there is a cycle, obviously it is not a suitable situation for prerequisites. So my situations like a prerequisite of the courses, etc., they will have no cycles at all. And obviously, if there are no cycles, only then I can have some course which can be started without any prerequisite. Won't have any cycle. So that is obvious. So I say, if I have a DAG, then topological sorting effectively means that we are going to sort them or arrange them as per their direction based or edges and their direction based. Edges, the vertices effectively based on the direction of edges. What does that mean? It will be more clear when I define formally topological sorting. So topological sorting says list vertices in a horizontal order such that all edges of the graph of the DAG have their direction always from left to right. From left to right. Meaning, like there could be C programming as one course. Before that, even could be digital system design, anything like that. But DS will guaranteedly appear on the right side of a CP. Algo will guaranteedly appear on the right side of a DS. Could be here, could be not here, could be in between also, anything. But Algo cannot appear before that. So maybe I say Algo here. Maybe I could have written here COA. So that will effectively mean whatever edges earlier I have drawn, though all those edges always have a flow towards left to right, from left to right. And all courses will be listed in the horizontal order. The advantage will be you can choose your courses in this order. Choose your course only if its prerequisites or edges from the left side are already covered. So if these are covered already or studied already through those the corresponding vertices, then you can choose your course. So university software will check for this. So this is what is called as a topological sorting. So how to do that? Things are very easy. The logic is simple in this case. Effectively, I can have whatever word I'll not say, I'll write the pseudocode. So if I say topological sorting, effectively the logic is nothing big. I say the directly sum traversal algo can be useful. And if you remember, in case of a DFS, what we did, we kept on traversing. Whenever there was an outgoing edge, we kept on going depth. And if there are no cycles, ultimately we will reach to a vertex which has no outgoing edges. Ultimately, we will reach to this vertex. And because it's acyclic, so there will be guaranteedly some vertices which will have never any outgoing edge. There will be some vertices which will have no incoming and some vertices which will have no outgoing. So once we reach to that vertex, this completes first. This such vertex will complete first. And I will say this will be actually last vertex in the topological series or in the topological order. This should be the last vertex. Then the previous complete will become obviously just before that. Previous completed can become the previous one. So that will become second last and so on. So that gives me a clear idea that what is the reason and how DFS can be used. So now I say, effectively, I will apply DFS with a change, with another step. And what is that step? That I will say in main DFS, not in DFS visit, I'm saying in main DFS, or I'll say in main DFS, or you could say not in main, I'll say even if we can do this in DFS visit, I will say that with another step in DFS visit. And what will be that step? That the completed vertex, what is this step? Is this the completed vertex is inserted at the beginning or at the front of the output list. Output list effectively topological series say that it will be a linked list. So effectively at the beginning or in the front of that list, you will insert the completed vertex. So this step will be the additional, and obviously at the beginning will mean that the vertex which is completing first will be the last, next completed will come in the next to this, and so on. For example, what does that mean? Let's understand. Let's assume I have some graph like this. So I'll just rename them. Say, let's say this is some vertex C, this is some vertex B. Let's say I have some vertex D here, I have some vertex A here. This kind of a dependencies exist. Say I have E here. From E, I have, let's say, F here, I have F here, and then maybe, let's say, I have G. I have such kind of a graph. Let's say, obviously, it is a DAG. So over this graph, we are going to do the DFS. So how DFS will be applied? Let's say start with A. Anywhere it will start because DFS can start with A. Let's say we start with A. So you started from A. You will be traversing its all outgoing edges one by one. So this is one outgoing, this is another. Let's assume you went towards E. So I say I went towards this direction. I'm making the double line where direction which I am going. So initially it is like this. And this side I have, so I have this connection originally. So I say this was there. So whichever direction I am going, I'm just making it a double. So I said go to E. So in DFS, initially A traversed. Of course, I want to display now because I'm going to store the output. But let's note down the traversal sequence. From A, I went to E. So from E, again, I will go to some outgoing edge. E has only this outgoing edge. I will go towards F. Going F. Now going F, and then I have no outgoing edge. And you can see F is effectively having the last vertex. It has a lot of prerequisites, but F is not a prerequisite for anyone. So I say after this, F gets completed. Completed will mean I have my output list. Output list initially empty. F gets added to this. From F, then I backtrack to the previous node. From backtracking happening to is E. E has no further outgoing edge. E also completed. So E completed will mean E gets appended to the linked list. So I have this linked list. It is a linked list, and at the starting, I am inserting every time. So E gets here added. From E, again, backtrack because E is completed. So I backtrack to A back. From A, now I say there are one outgoing edge towards F. F is untraversed. I'll go towards F. F is already traversed. So nothing of going in that direction also. So A will also complete. A complete means A also comes here. Then now I have to resume from somewhere. So your main DFS comes. From main DFS, you will be now starting your DFS visit again from B. Then you start with B. B is displayed here, or I am not displaying. I reached to B. From B, go to the outgoing edge of A. Not possible. A is already covered. Then go towards G. You can easily see G is also last, but G could come anywhere. The only thing is we have to ensure the topological ordering. So now from B, we go to G. G, nothing out. So G completed. Completed means again backtrack, and before backtrack, put it into the linked list. So G comes here, connected like this. So this is the order coming. From G again backtracked, coming to B. B is completed. Let's say now I will start with another vertex from the main. So main DFS will again activate, start with the C. From C, one outgoing is B, already traversed. So I'll go to D. From D, go towards E, already traversed, nothing to be done. So D will be completing now. D will come here. So I'll just remove these words and write here. So D will come here, connected like this. Then similarly, C will come connected like this. So now if you see, if I have these vertices and try to see their all edges in between, in this order, I can see that if I have edge C to D, one edge, I have C to B. So B was somewhere after this, before, after G, B will get completed. So from C to B also I have an edge. From D to E also I have an edge. From E to F also I have an edge. From A to E I have an edge. From G no edge. B to G I have an edge. And you can see all edges are left to right. So this is what this topological sorting means. So without much special logic, my topological sorting straight away works. If I have to do the analysis will be simple. I know that the first step or main step is a DFS step. So DFS step, we already seen that the time complexity is a theta of V plus E. Then extra step in DFS, visit is insert at the beginning, insert node at the start of linked list, at the start of linked list. And I know that if insertion is to be done at the start of linked list, this is theta of 1, big of 1 or theta of 1. So total time complexity is straight away theta of V plus E. Extra space complexity, yes, order of V, because I'm storing the output in some list, either store it in a linked list or store it in an array or store it in a stack, one and the same thing, but it will be theta of V precisely, because that much extra nodes, extra array, extra stack will be needed to store the output list. So output list will be stored in this. So that's it. That's a simple one. So topological sorting has its own usage. Then going further, we will see another interesting algorithm, which we are going to see today. Again, that is very useful in the social network. So earlier, there were limited applications in the IT domain. Of course, mathematical or research domain, this algo has applications, but rarely in the industry. But now it has a lot of applications. For example, I say that out of class of 100, I want to find out that make their groups of students, make project groups. And for project groups, we would like to ensure that the students which are friendly to each other, they should be in a single group. So group must be cohesive group. There should be no fights, or they should be relatively comfortable with each other to work. How they will be cohesive? For example, I say if student A is a friend to B, and if let's say B is also friend to C, and maybe if a C is also friend to A, so then probably I can say ABC can be made as a group. Maybe if I say D is friend of A, but D is not a friend of B and C, I don't have any connection between D and B, so I'll avoid D to be in this group. I want they must be friendly to each other. Then how to find this? So such to activities, etc. Or when you go to the LinkedIn, say if you want to find out all those students who like competitive programming of BTech CSC third semester, they should be grouped as a single team. Then I need certain storage and certain algorithms similar to this. So on Instagram, when you see certain common liking tastes, some taste-based grouping, or on Facebook, or on Twitter, or etc. We can have these usage, and maybe even LinkedIn, etc. So such concept is called as strongly connected components, and we are going to see algorithms towards this. So it is called as strongly connected components, or in abbreviation called as SCC. So SCC is now has a lot of social networking applications. Similarly, in case of a topological sorting also, it can have social networking applications. Say on Twitter, I want to find out the starting person who has started a hate speech, starting or source of hate speech or hate message. Then if I have some algorithm like topological through which I could start that this person has sent a message to this person received this message from this. So I can backtrack, and effectively, if I have a topological sorting, the initial nodes can be probably quite useful to find out who initiated these kind of hate speeches. So over Twitter, if some data structure and storage and those dependencies are maintained, and we store this information and then apply something like topological sorting, many of those things can be useful. So that was application of topological sorting, and SCC, we have already seen the different applications. So let's now make strongly connected component and its logic and working. So we will have the logic and working made, and we will understand what does this define. So first of all, let's define definition. So my aim is that all vertices, so first thing is obviously it's going to be a directed graph, not only directed with the cycles, because through cycles only the complete cohesiveness or connectivity will be ensured. So we say it's a directed cycle, a directed graph with cycles. And out of this, what I want my graph to be subdivided into multiple, or I'll say all vertices are to be grouped into multiple components, to be grouped into various components, let's say C1, C2, C3, etc. C1, C2, C3, and so on, such that all vertices, or I'll say not all, I'll put it in another word, I'll say every vertex of a component is reachable from all other vertices of this component. And what does a reachable mean? I'll explain. So reachable means we show it as U to V. So I say there is a path from U to V. And path means one or more sequence of edges. For example, if I say that there is a vertex A, there is a vertex B, there is a vertex C, if I have a connectivity like this, then I can't say ABC as a component. It will be incorrect, because from A to B, yes, there is a path and reachability. A to C, yes, there is a path or reachability. B to C, yes, but B to A, I can't reach. C to B, I can't reach. C to A, I can't reach. So it is incorrect. On the other hand, if I have the same thing as, let's say, A, B, and C, and if they are connected like this, then I can say, yes, from A to B, direct edge exists. From A to C, I can have A, B, C. So this A to C is also possible. From A to, for all, then next I will say, let's try for the other nodes. So I'll say for B also, P to A possible directly via C. B to C is a direct available. Okay. C to A direct available. C to B, yes, via A I can go. So there is a path. So then I can say A, B, C can become a connected component. Similarly, there can be many more also. So having said that, let's take an example, and based on that, we are going to use the algorithm and make the logic for this. So for better understanding, I'm using the same example as it is used in the book, so that from the book you can revise also. So I'll say in the book, the example they have taken is A. They have 8 nodes, B, C, D, E, F, G, H, and the connectivities which are given there. I am drawing, taken from the book directly, and they have like this. Then I have like this, this one, and this direction reversed. This one, they have this connection, and I have G to H also, and I have one more connection like this. So this is a book example of the book. Now I say, let's say I have this particular graph available and I want to find its strongly connected components. So what is the logic behind that? Of course, either I have to think of how can I find, but because you are starting with the algorithms, so it will be easier to you that initially you understand what is the process of finding this, and then programming you can do, but that will tell you how to find in which case a DFS is useful, in which case a BFS is useful. So effectively, first I will tell the solution. So SCC logic effectively says first step is apply DFS. Again, it's a DFS application over the graph. And second step is find transpose of the graph. And the transpose of the graph will mean effectively we show it as a G raised to T. So transpose, let's say a new storage we can generate. And then I'll say, now apply DFS over G raised to T, but with the order in main DFS to be slightly different. In main DFS, the order to be in decreasing order of finishing. Decreasing order of finishing in step 1 of step 1. Means effectively, during step 1, the topological sorting order is needed. Topological sorting order is to be used. Topological sorting order for step 1. So effectively, it means after this, store its a topological sorting order some way, either a linked list or a stack or whatever, and then the same order to be used in main DFS instead of 1 to n, the order will be this. This will be more clear once I have that graph to be used, and then we will be showing why this logic happened like this. Let's use the same graph which we have just drawn, and I will have this graph, let's say, redrawn here so that it will be more applicable or useful. So I say I have here A, I have here B, I have here C, I have here D, then I have here E, I have here F, G, H, and I have effectively connections like this. like this one. Then I have a connection in between CD, and I have in connection between this, and I have a connection like this. So this is the graph. Now I say first step, DFS over this. Say main DFS starts from C. Although we can take it from A also, but I'm starting it from C, and that C onwards the starting will mean that I'm going to use it. Let's say this was vertex number 1, indirectly numbered, and then maybe let's say this was vertex number 2, this was vertex number 3, 4, 5, any numbering could have been here. So whatever you say, this numbering means in your main you are using this ordering somewhere. Doesn't matter. You can start from anywhere, results will be same. So let's say main DFS starts from C. Now, I am going to effectively generate their topological order. And so DFS starts. Let's go one by one. What happens? Initially, 1 started only. And from, I'll say 1, instead of this 1, I'm writing C. So C is the node. So I am just removing now 1, 2, 3 so that you don't get confused. I just said that we started with 1. That's it. We started with the C vertex. That's it. So rest everything is the same. So this is the start. So started from this, C has just started. After C, we will follow its outgoing vertices. Let's say it has a C and G both sides, G and a D both sides. Say assume then you went to G. From G, again it has outgoing edges towards F. So I'm just doubling to show which direction I went. From G, I will go to F. Now from F, no outgoing, so F will complete. As soon as F gets completed, I will put it into the topological sorting order. Let's assume either I have a linked list, or because now we don't need explicitly linked list, SCC doesn't need that output list for any purposes. So I assume let's have a stack. Stack will also do the same thing because in this order I will store. So F completed is stored initially. From F, the next you resume at, let's say, G. Then you are back to G. And from G, you go towards H because this is the outgoing edge. So you have then H here, and H will be completed over and then completed, and then you will be backtracking. So H I will store into this. It is effectively topological sorting order. From H, you backtrack to G again. From G, nothing more to be traversed. You backtrack to C again. You reach to C. From C, you can go towards a D. So you will go towards a D, going towards a D, and then nothing more to go from D because H is already covered. So means nothing else to be done. So finally, D completed. So D completed, I will have now after this, after this, firstly, initially I have G also completed. So after F, H, I said G also completed, only then I went to C. So G also stored into this. Now D completed, D stored into this. Then back to C again, resumed at C. C has no outgoing further edges for untraversed vertices. So C also completed. C completed, again backtrack. C was the starting point, so no question of a backtracking of this. We are already at the start. Main DFS resumes. Main DFS resumes means now another node will be selected. Let's say main DFS selects next node as this. So now we start with B. So my B will be started. From B, I can go either towards E or I can go towards F. F is already covered, so no question of going this side. It will mean I will come this side. I'll just remove this so that there is no confusion. So this now I start in this direction. I go to E. So E I reached. From E again, it will use its outgoing edges. F is already traversed, so nothing to go this side. So the only choice will be go towards A. So A I go, and once I reach A, outgoing of A to be gone. B is already traversed, no else outgoing. A will complete. Completed will mean A gets pushed into the stack or added in the beginning of the linked list. Then you resume at E. E has no further outgoing, so E will also complete. E gets covered here. From E, then you will resume at B. B has outgoing this side C already covered. B has outgoing F already covered. Nothing else to be done. B also completed. So B comes here. And after that, resume back. No backtracking possible. So this also no resumption possible. Then your main DFS finds no pending vertex, no uncovered vertex, and O. So this particular order is ready. This is my topological sorting order ready. And I have this stack or linked list to be used further. Then will come that I'm going to make the corresponding graph to be reversed, transpose. So transpose of this graph, G raised to T. So how it will appear? Let's say I have A, B, C, D, E, F, G, H. So C to D and D to C direction change will not make much of a difference. They can already have this. Earlier, this was the direction, so I have reversed. This was reversed. So earlier I had this way, now reversed. This also reversed. This was like the earlier reverse. So now this and this. So I hope I have redrawn correctly, and let me just have a look with the previous graph. Yeah, everything is fine, and we have this edge also. Yeah, so now this, but the only thing is the processing will be always, so let me just have this somewhere there. So my stack will always come into picture. So in the previous stack, I have the data. Let me just see the name ordering B, E, A, C, D, G, H, F. So I have here B, E, A, and then C, D, G, H, F. So C, D, G, H, and F. So my main DFS now will start in the order of topological sorting order, or I'll say decreasing order of finishing. The one who finished the last, that will be the first to start. So B was the last to finish. B is on the top of topological sorting order on the top of the stack. So I will push the pop from the stack. B will be taken and the DFS main will start from B. So from B it starts. B is there. From B, it's traversal to be done. The only choice available is go towards A. If you go towards A, obviously A is traversed. From A, the only choice to go is towards E. From E, I will obviously reach E. And then from E, I can go this side, but B is already covered, so nothing to be done. And then I say backtrack. From E, backtrack to A. At A, I have nothing else to be revisited, so backtrack to B. I backtrack to B. B has no further outgoing edges, backtrack further. No backtrack possible. As soon as no backtrack possible, now in main DFS, I will have a slash and also added. This one component is ready. So whenever one iteration or one recursive version of DFS visit is over, one component is ready. So for showing the clarity, as soon as one component over, before next main visit call, I will print slash n. Now main DFS resumes and slash n given. Next line I have come. It will say Which order? Order has to be from the stack. So E will be taken out and E to be traversed first. E is already traversed. A will be taken out. E is already there. Now you could easily see A was here, E was here, and B was here. This was the relative connectivity possibly in the original graph, and in the transpose also they could get covered more or less in the similar order, and hence they became a component. Going further, this I'll explain after a few more minutes. So effectively, this is removed, this is removed, this is removed. Next to be removed will be C. So C is uncovered. Resume your DFS visit, or DFS visit starts with the C. From C, the outgoing is only towards the B. So only towards the D. So D will be visited. From D, no outgoing. D completed. Backtrack to C. C, no outgoing. Over. Further backtrack. No backtracking possible. DFS visit over. Again slash n coming. Now again resume from the main DFS. Main DFS is going to do this. And again take out D. You could see CD were consecutive here, and they are further able to be further connected. Then take out G. G is untraversed. So start from the G. Take G here. From G, then you have to go for its adjacent. G's adjacent is F. Go towards F. And from F, you will see only this side to go, nothing to do. So F complete. Backtrack to G. Backtrack to G. You can't go towards the C, already covered. So G also over. And when F was completed, and to F, printed F, then backtracked from F, backtracked from G, no backtracking possible, GF over, slash and take. Now go to the main DFS. Main DFS pops out H, already not covered, so H will resume. H covered. From H, outgoing is towards G, nothing to be done. Outgoing towards D, nothing to be done. H over. Backtrack, no backtracking possible. This is also over. Maybe you have a slash n, but nothing left. So effectively, you have now your components ready. BAE being one component, CD being another component, GF being another component, and H being another component. And the whole logic behind this is simple, that in G, whatever connected component existed, they will also exist in G raised to T. Same components will guaranteedly exist because collectively they make a cycle or reachability from each other. Same components will exist here also. And that helps in a way that from initial DFS, you could find certain connectivity, like let's say saying B, A, E were connected in a direction like this. From BAE, the direction which was able to be followed was effectively something like this. Over G raised to T, you could effectively find whether EAB will also be possible or not. So if you could get the same connectivity and same traversal possible in sequence repeatedly in the transpose as well as in the original, then they deserve to be called as the same component. And that is why the concept of DFS with graph transpose also used to solve this problem. So the whole basis has been that firstly, I applied DFS to find one direction of connections or reachability of one directions found, or reachability of one particular way. Directional connectivity was identified. So it was unidirectional identified. Other side I was not able to find out. Then I reversed the direction, reversed the directions, and again order of the DFS previous order onwards I supplied that previous order based previous ordering based traversal of DFS over GT based traversal, or I'll say DFS over transpose over reversed direction, helped me to identify the reverse directional reachability. This identifies reverse the reachability. So reverse reachability also ensured. Original initial reachability was also identified through original DFS. So this reverse reachability guaranteed, confirmed, and only then they became the strongly connected component. So its analysis also you can do easily. Programming also you can do easily. Effectively, if you have implemented topological sorting, also implemented transpose and store transpose. So I'll say for this, I'll just say programming is easy. DFS you have already implemented. So with DFS, first of all, you have DFS with stack or topological stack entering order to be stored. Then after this, have the transpose logic. So transpose you can implement, and simple way can be store in another graph so that you don't face any complications in generating the transpose. Store it in another graph and then apply DFS over again with G raised to T graph as input, but main DFS order to be ensured. Main DFS I will be based on pop stack. And it will say while stack not empty. So while stack not empty, you will find out I, and then DFS visit over this I will be attempted if it is uncovered. So this can be the logic, and not a difficult logic. This time complexity, we already know theta of V plus E. This complexity is also remaining theta of V plus E. So I'll leave it to you what is going to be its time complexity. If it is more than V plus E, obviously total complexity will increase. If it is less than or equal to V plus E, overall time complexity will be accordingly found. So overall complexity you can find based on knowing how to find out a transpose and what will be that complex. Having said that, I'll stop here and try to implement a topological sorting as well as strongly connected component. You can use the same concept still without much difficulty. Just to add one more line to your understanding, in the book, you have this same example explained. It uses the concept of time of travel, time of discovery. So it says the time of a start of a vertex, which they call is the TD. In the DFS, TD time and time of a finish is used, which they call as a TF. And based on TF, effectively ordering is done. Based on decreasing order of a TF, second DFS is applied. Based on decreasing order of a TF, the step 3 is applied. So it is one and the same thing, because instead of using this TF, we did not use this explicitly, and indirectly we have already done that by storing it into stack, which automatically work the same way, but we also use the same finishing order. Finishing order in the decreasing order we also used indirectly, either in topological also or in case of the strongly connected. So it is one and the same thing. So you have a choice whether you want to use your TDTF or you want to do like this. This becomes easier, so you can still do with this and you don't face any problem with this. Having said that, let me wind up. Bye-bye. All the best to all of you. And I'll again suggest that you must implement all these and then only you will be able to appreciate these logic.